Değerli katılımcılar, değerli dostlar, sevgili öğrenciler, sizlere en içten dileklerimle, saygı ve sevgiyle selamlıyorum. Bilindiği üzere 2020 yılı başlarından itibaren insanlık neredeyse aniden COVID-19 koronavirüs salgını ile baş başa kaldı ve hayatımızın her alanda zorlaştığı bir döneme girdik. Dünyada ve ülkemizde birçok araştırma ve eğitim etkinlikleri, toplantılar, çalıştaylar, yaz okulları iptal edildi ya da ertelendi. Bu duruma ilişkin oluşan bilimsel izolasyonun motivasyon kırıcı etkilerinin yaygınlaştığı bir dönemde TÜBİTAK Temel Bilimler Araştırma Enstitüsü faaliyetlerini çevrim içi ortama taşıyarak var gücüyle devam ettirdi. Bu faaliyetler temel bilimin çeşitli alanları ile disiplinler arası alanlarda toplam 6 ayrı ileri düzey seminer serisiyle bir bilimsel Türkiye popüler konuşmalar serisi şeklinde sınıflandırılarak gerçekleştirildi. Nobel ödüllü bilim insanları başta olmak üzere dünyaca ünlü bilim insanlarının katkılarıyla gerçekleştirilen bu etkinliklerde ilgili alanlardaki en üst düzey ve yenilikçi bilgiler ülkemizin bilim ve eğitim camiasına aktarıldı. Bugün gelinen noktada enstitümüzün yüz yüze seminerleri de başlamıştır. Ancak pandemi döneminde başlattığımız uzakları yakın eden ve zorlukları fırsata dönüştüren çevrim içi seminerlerimiz de devam etmektedir. Bu akşam yine bu vesileyle bir araya gelmiş bulunmaktayız. Bu akşamki seminerimiz kimya bilimleri seminer serimiz kapsamında ve İsviçre Federal Teknoloji Enstitüsü'nden çok değerli bir bilim insanı Profesör Maksym Kovalenko'nun katılımıyla gerçekleştirilecektir. Maksym Kovalenko, kurşun Halide Perovskite Nanocrystalları ve Superfluorescent süper örgüleri konulu bir konuşma yapacaktır. Seminerimiz İngilizce olarak gerçekleştirilecektir. Dear participants, dear colleagues and friends, dear students, a very warm hello everyone and good evening. It is my pleasure to welcome all of you to this episode of the Chemical Sciences Seminar Series of TÜBİTAK Research Institute for Fundamental Sciences, with the participation of Professor Maksym Kovalenko from the Swiss Federal Institute of Technology, ETH Zürich, Switzerland. Professor Kovalenko is a distinguished scientist and world-class expert in the field, as well as a wonderful person. He's going to give a great talk on lead halide perovskite nanocrystals and the superfluorescent superlattices. Maksym Kovalenko is a professor of inorganic chemistry and the head of the functional inorganic materials group at ETH Zürich. The research activities of Maksym Kovalenko and his group focus on chemistry, physics, and application of inorganic solid-state materials and nanostructures. In particular, present research efforts concern the precision synthesis of highly luminescent semiconductor nanocrystals, nanocrystals surface chemistry, exploration of novel semiconductor materials by solution and solid-state synthesis, novel semiconductor for hard radiation detection, novel materials and concepts for lithium-ion and post-lithium-ion rechargeable batteries. Many of these activities are strongly linked to industrial partners. Professor Kovalenko born and grew up in Ukraine, Bukovina region. He studied chemistry at the Chernovitsky National University and then continued at the Johannes Kepler University, Linz, Austria, where he obtained his PhD in 2007 under the supervision of Professor Wolfgang Hayes. Subsequently, he joined the University of Chicago for postdoctoral training with Professor Dmitry Talapin. He joined ETH Zurich in summer 2011 as a tenure-track assistant professor and was promoted to an associated professor in January 2017. And finally, here he became a full professor in 2020. Professor Maksym Kovalenko has received a number of honors and awards, including Rössler Prize, highly cited researcher in 2018-2019, European Research Council Consolidated Grant 2018, Werner Prize 2016, and Ruzicka Prize 2013. With this, I want to invite Professor Maksym Kovalenko to stage to begin his talk. Maksym, please come. We are very honored to see you, and it is a very pleasure for us to see your title in Turkish on your slide. Thank you very much.
Thank you very much for your introduction and for such an honor to speak to such a broad, geographically and scientifically audience. It's my great pleasure. So, as just announced, I'll speak about the specific topic in our group, which is perovskite nanocrystals. And so my goal is to basically begin with the journey, how we started to work with these quantum dots from historic perspectives through the lens of our own experience. And then I will bring you to the most recent work, including unpublished results. And so it will hopefully cover the needs for those who just want to have a little bit of glimpse on the field, as well as those who might be working. I know in Turkey there are people working on perovskite nanocrystals, so those might enjoy then the most recent results. So this is our group. So these are the people who actually work on this topic in our group, and so actually you see here also people from Turkey back here, Turedi and Yashim. So just to advertise right away that we are always happy to if there are young, talented and motivated students, postdocs applying to our group from Turkey, we will definitely consider their applications and always respond to them. Now, so as you can see on this T-shirt of on the group members, this was a celebration actually of our group 10-year last summer. And so on the T-shirt, you see that perovskites have become one of the most interesting materials for us, both from the basic research point of view, so nuclear magnetic resonance, to applications such as light emitting diodes and photodetectors, for example. Now, 1 second. Yeah. Okay, and I would like to also acknowledge the funding sources which support our research, as mentioned, from ERC to national and international funding agencies. So, for those who would like to hear a little bit of the history of quantum dots, well, it's a 40 years old history from the initial discovery of quantum size effects. But if we talk about colloidal nanocrystals, colloidal semiconductors, the first milestone was in 1993. Cadmium sunlight quantum dots had been produced in a very monodisperse form as a colloidal dispersion. So basically, you have inorganic core of one material, calcite, coated with organic monolayer of another material. And so basically, this research had been super fascinating since early on, because simply by changing the dimension of these nanocrystals within the few nanometer range, you could tailor the band gap energy through the quantum size effects, and therefore the color of these dots covers the whole visible spectral range. So that was super exciting. And if some of you wish to learn more about nanocrystals in general, they have, well, 3,000 years old history, and that's what we recently published in such a sort of historic perspective. But speaking of semiconductor nanocrystals, which we call quantum dots, these are roughly 30 years old. Now, what was also not super exciting from the beginning was to notice that the light emissive property of this quantum dot was not that great at all. And the problem back then was that that quantum dots as produced, they do not exhibit bright luminescence. And luminescence, as you know, this is a reversal of the absorption, right? So that photo-generated electron-hole pair recombines back. And the big hope for these materials was that they will emit light with high luminescence quantum efficiency, and therefore they can be used as inorganic nano-sized light emitters. But they turned to be very bad light emitters as produced. And the reason for that was that the surface which quantum dots have, you know, they have very high surface to volume ratio. And the surface is basically made of dangling bonds. Basically, you cut the lattice, you create dangling bonds. So basically orbitals which are not binding and not anti-binding. And so they are mid-gap states, right, which exist localized on the surface. And they are capable, even in a very small quantity, they are capable to quench electron or hole, therefore, thereby basically preventing efficient luminescence. So what people have done since very early on, they focused on how to resolve this problem. And the first high quality demonstration of this concept of core shell nanocrystal goes back to Philippe Giossioni in '96. What he showed is that if you now take this quantum dot material and overgrow it with another semiconductor, which has a wider band gap, but the same crystal structure, you can actually now decouple in space the existence of these dangling bonds at the surface and the localization of electron and hole wave functions to the core. The simple concept turned to be experimentally demanding because you need to sort of maintain monodispersity, you need to homogeneously in 3 dimensions overgrow the nanocrystal, and you better also create a graded shell so that the band gap gradient is smooth and that the overall quantum dot size is sufficiently large to fully decouple the surface states from the core. So it actually took about a decade to engineer quantum dots to such quality that they have been then utilized as phosphors in the television displays. So by now, this application in television displays is by far the most important application of such semiconductor quantum dots, which are emissive in the visible spectral range. There are also infrared applications, which we will not discuss much, but those then extend to, let's say, infrared cameras, where they do the opposite function. They absorb light and they generate electron hole pairs. But here today, we focus exclusively on the probably main property of quantum dots, which is light generation. And so what you see on the market is that 3-5 based quantum dots lagged slightly behind initially, but then they caught up and now they are the dominant quantum dot television display technology from Samsung, for example, but also a few other companies. So all these dots which you see on the screen are commercial products, and you see them in some of the best quality LCD displays best quality in terms of emission colors and energy efficiency and so forth, and brightness. Now, we were used to believe that this playground is basically just 2,6 and 3,5 compounds until 2013, when these semiconductors known as lead halide perovskites have been rediscovered as optoelectronic materials. Initially in the semiconductor solar cell as a semiconductive absorber for solar cells. So just to briefly introduce, they are called perovskites because they have exactly the same crystal structure as oxides, which have perovskite crystal lattice, such as calcium titanate, but they are not made of those elements. They are made of lead and halide. So the valences here are a factor of 2 smaller than these, but the crystal structure is the same. So that's why they are called lead halide perovskites. Now, those again have band gap tunable across the visible spectral range, here by composition in the bulk form. And so, so you might know that this should not have appeared here. This was so basically the quantum, the color conversion efficiencies. Sorry, not color. The power conversion efficiencies of these perovskite-based quantum dots, perovskite-based absorbers have become comparable to the classical semiconductors such as gallium arsenide, silicon, and cadmium telluride. And so back then, in 2013, we understood that inherently halides make for a good semiconductor. So why don't we use them now as a coating for perovskite for conventional quantum dots? So we take a perovskite as a shell to coat the conventional quantum dot instead of using the core shell strategy. And so that was super exciting because we were able to use these soluble forms of these perovskites, they are called halometalates, to use them as a surface capping ligand. So we displace organic ligands, we cover the surface with this halometalate coating. And because of that, we could basically fully change the surface functionality from apolar to highly polar, and that you see from the dispersion of these nanocrystals. They migrate from the apolar phase into a polar phase upon this ligand exchange. And what was extremely important back then is to observe that such an exchange can preserve or even improve the electronic state of the surface. So somehow it turned to be very beneficial to have halides at the surface as compared to chalcogenides, for example. And so that you see from the retention of high quantum efficiency for the luminescence in the visible and in the infrared spectral range, and so forth. So this on its own has become a very popular research area because you can have now quantum dots which are fully inorganic and which you can then electronically connect to each other, and they still maintain intrinsic semiconductor nature, so they are used actually in such quantum dots capped with halometalates are used in photodetectors and solar cells and some other applications. But we will not focus on those. We will just proceed with what we did as chemists. We understood that, okay, if a perovskite is good as a coating for the usual quantum dot, why don't we make the entire quantum dot out of perovskite? So that was our entry point into the world of perovskite quantum dots. And since then, we basically keep working on that because everything we do since then is super exciting, and I will share with you some of that, of those observations. So in 2014, we began to work on colloidal synthesis now of perovskite quantum dots. We focused initially on cesium lead halides fully inorganic. And simply by reacting two very simple precursors, in the presence of such long chain molecules, you produce nanocrystals which are cubic in shape and which are quite monodisperse. And it was easy to extend this simple synthesis to basically the entire family of these lead halide perovskites, which is formamidinium and cesium based. And what was super exciting back then, that as you produce them, they emit very bright light. So you don't need to overcoat them with any other semiconductor. As they are bright emitters, because apparently their surfaces are relatively benign, as they don't introduce mid-gap states. So, and that is the first example of wideband gap semiconductors whose surfaces are relatively benign with respect to the electronic behavior. So what was also very exciting is to observe that now you can mix different ions and create multinary perovskite nanocrystals, which is that you can mix A site, cesium and formamidinium, or halide, so you can have solid solutions, and therefore you can control the band gap by composition. So you can have phase pure multi-component nanocrystal, which is very difficult to do with chalcogenates, for example. So you may be wondering why they are always cubic shaped. That has something to do with both, with the intrinsic crystal structure, because perovskite lattice is derived from a cubic-like crystal structure, but it's also essential to consider which surface facets are stable. And so in our first synthesis, as you might recall from this slide before, we use primary amine, which converts into ammonium, a long chain alkyl ammonium capping ligand. And another example is shown on this slide, which is dialkyl ammonium. So this is ammonium group, which is positively charged, and two alkyl chains. So these cationic surfactants or ligands bind to the surface by displacing the surface cesium ion on the 1,0,0 terminated crystal plane. And so just replacement, let's say, of the 50% of the surface cesium yields such a stable surface facet. And so because of this mechanism, your nanocrystal definitely prefers to expose only 1,0,0 facets, and therefore you end up with a cubic shape. As a little spoiler, I will show you that you can actually use some other ligands, and therefore you will have different shape. But in the initial first edition of this material, we had a cubic shaped nanocrystals. Now let me start speaking of the problems now. Before you understand the problem, let me show you how the synthesis looks like. You inject cesium oleate into lead bromide solution, and you see immediate appearance of quantum dots. They are green emitters. So the reaction is completed within the mixing rate, which looks very exciting, right? So you very quickly can produce grams or kilograms of these quantum dots. At the same time, such a fast reaction is a problem if you want to have very fine control of the size, especially down to very small sizes, or if you want to grow some heterostructures and so forth. So for about 6 years from this initial, the first edition of the synthesis, we used only this type of chemistry, which was very fast because the ions co-precipitate very rapidly. But then 2 years ago, we began to explore a new synthesis pathway, which allowed us, and I show you the outcome of that new synthesis, which was just published last month. Here you see that you can actually have this whole synthesis much slower. So you see this absorption spectra of these quantum dots measured within 30 minutes. So this whole progression is half an hour instead of 1 second or less. So now you have a synthesis which is much slower, much easier to control, and everything occurs at room temperature. So you don't need to even heat it up. So you may ask, what did we change? So the idea here is that we avoid using any amine in the system, because when you have amine, it will become ammonium. And if you have ammonium, you will need to have a counter ion, which is lead bromate, cesium lead bromide 3 minus, lead bromide 3 single minus, which is too reactive. So you better do not have active ionic species in the solution. You should go as molecular as you can, and therefore you will have much slower nucleation in growth. One way to accomplish that, and I believe there are many ways to accomplish this, but one is that you, again, you don't use any amine. You use lead bromide and triactylphosphine oxide as a molecular adduct, which dissolve at room temperature in hexane, and you injected cesium salt. So only cesium in this synthesis is in the ionized form, more or less. The other precursor is fully molecular. And you see the absorption spectrum of this lead bromide topo adduct in the UVV spectrum. Then, as you mix them, they slowly start to react, forming lead dopa, which is phosphinate of some kind, doesn't matter too much, and an actual intermediate. So now you form this cesium lead bromide, but not a lattice, but a conglomerate of ions, which is cesium plus and lead bromide 3 minus. It's a 3 nanometer large chunk of ions which are pre-aggregated, and then they slowly recrystallize into the nuclei of the nanocrystal, and then you form a nanocrystal. So that's our current understanding of the mechanism. Beauty here is that for lead bromides, you can actually observe all the relevant species in situ during the synthesis. Precursor itself, then at slightly smaller energies, you observe this intermediate, and then finally you observe the quantum dots. And so just by measuring in situ optical absorption spectrum, you can actually recalculate these features, their intensity, their optical density, into the population of every species, so you can track the mechanism of the reaction. And just to give you an idea, you can actually observe that your nanocrystal size, quantum dot, your nanocrystal quantity will rise, the concentration of quantum dots, and then saturate. That means you have reached the plateau in your concentration and in your size. That you know then that at this moment of time, the whole reaction is finished. And then you can isolate your nanocrystal in a high yield. So just to give you an idea, this synthesis is so much more convenient and better controlled that we now entirely shift to this approach. Now, one of the reasons why this synthesis is beneficial is that you can also expand it to hybrid perovskites, which have been traditionally very difficult to produce because they are much more fragile. And now we can produce formamidinium lead bromide or methylammonium lead bromide with the same degree of the size down to very small sizes. So with this new synthesis, you can isolate extremely small nanocrystal sizes down to 3 nanometers in a large quantity and with retention of the stability throughout the purification. But what's also very special is that your dots are no longer cubic, they can be of spherical shape. And the reason here is exactly what we discussed before, is that you no longer use amines in the synthesis. So this mechanism of 100 lattice plane stabilization doesn't hold anymore. You don't have any ligand which binds very strongly in this system, which is a blessing and a curse. It's blessing because you can actually then use such a synthesis for as a first step to functionalize your nanocrystals with any ligand that we want. You can put then any molecule that will have high affinity to the surface, because in the synthesis you don't have any such molecule. So you can decouple the formation of nanocrystals from their subsequent surface functionalization. The curse, of course, is that you have to do it rapidly, because otherwise nanocrystals after the growth will start coalescing and recrystallizing to bulk material. In this case, right after you reach the plateau in the nanocrystal formation, you now add the ligand of the choice, and you can stabilize nanocrystals. And any ligand that we used before, but as well as any ligand which we will discover in future, can be now tested in a very rational manner through this approach. So this brings me to the surface studies. By the way, just to show you that you can also produce mixed halide compositions by mixing bromides and chlorides. You can then scale the band gap by the composition, or by size, or by composition. Now the most important part of the whole story is, of course, the surface chemistry. So, what is the problem with the surface chemistry of perovskites, and how to resolve it? Most of nanocrystals, cadmium selenide, gold, nearly everything, bind to the ligands through covalent bonds. Thiols, for example, on the surface of gold, they attach very strongly because of very strong sulfur-gold bond. Oleate on the surface of cadmium selenide attaches through rather strong carboxylate of cadmium bond. Perovskites are very soft ionic species. So you cannot play with the covalent attachment of ligands here, because if you attach something covalently like thiols, you will actually destroy the nanocrystal, because the binding of your ligand to your ion will be much stronger than between the ions inside the lattice. So you've got to deal with these ionic surfaces in a smarter way than covalent attachment. Now, as you've seen, when we use alkyl ammonium ligands, they do bind non-covalently. They replace cesium. So this is an example here, as we discussed before. Such alkyl ammonium displaces surface cesium ion and inserts the head group into this pocket. Now, similar approach you can do with anionic ligands. They will displace surface halide and insert themselves. But even bigger problem is that it's easy to overdo this, because as you add more of these ionic ligands, they start carving into your material, they etch it. And it's always tricky to find a balance. And so then we thought several years ago how to make it, to run this ligand functionalization in a rather softer manner, and yet bind our ligands even stronger. So we came a few years ago, we came to the idea to use sweeter ionic ligands, where this is a good example, where you have positive and negatively charged group in one molecule. And so now this group will attach to the surface by displacing a pair of cation and an ion at the surface. And that worked. So one example is lecithin. It's a natural phospholipid. You find it in chocolate and in many other products, very cheap. It works wonderfully. And so now we started to ask ourselves, do we really understand fully how these ligands actually attach to the surface, these sweeter ionic ligands? And because of our new synthesis, we thought if we better understand how the ligands attach, then it will give us some design rules how to engineer the head groups and the tails. And then we can attach all kinds of phospholipids to our nanocrystals and check the whole library of them. And so we now undertook over the last year or so mixed experimental slash theoretical study where we first analyzed how the zwitterion binds to the surface through molecular dynamics, and in parallel we started to test different head groups and different tails of these phospholipids and see how that allows us to make our colloidal systems even better. Without going too much into detail, I will just tell you that we tested several possibilities, such as attachment of a ligand simply by adhering to the surface, or displacive attachment, which we initially assumed, where the phospholipid displaces a pair of ions and incorporates itself into the AX-terminated 100 facet. So our conclusions are that this binding mode 3 is much more likely than any other one depicted on the slide. But most interesting finding was also to question whether this typical for phospholipids quaternary ammonium moiety is ideal or not. Because in principle, this is a permanently charged cation, and it sounds like it's a good group, but it's a little bit bulky for this site. And so we then checked, what if we take a primary ammonium group, which is 3 hydrogens instead of 3 methyl groups. And when you take this version, the one which is primary ammonia, so we call it PIA, so which is phosphoethanolamine. So this group is phosphoethanolamine. And just for the sake of language, this is phosphocholine, and this is phosphoethanolamine. We find that this ligand, because the size of this group is quite a bit smaller than the trimethylammonium group, this one binds much better to the pocket, which is initially occupied by cesium, and so basically it binds much better to the surface, such that you can actually have full monolayer coverage of the surface with a phospholipid of this kind. And so this correlates well with subsequent experiments. So what experiments have shown that indeed, if you take exactly same organic rest here and just compare the PIA group with phosphocholine group, like shown here, on the day 1, these colloidal solutions will look similar, but a few days later you'll notice a big difference because the PIA-based ligand desorbs much slower than the one which is phosphocholine-based. Basically, in good agreement also with the simulations showing this much more stable binding. Now, with this knowledge, we have tested the whole library of ligands. So we kept PIA-based zwitterionic phospholipid group, and we engineered a lot of different organic residues. And this is for the first time that you can have perovskite nanocrystals dispersible in basically every solvent that you may come up with, except water, because in water the material itself dissolves, the perovskite material. But now you can disperse perovskite nanocrystals in alcohols, in acetone, or in very apolar solvents. And you simply accomplish that by the group which you bind to your phospholipid. So let me show you then also another aspect, which is, excuse me, somehow, yeah. So this is how you make these ligands. There is extensive art of the synthesis of phospholipids, because in biochemistry and in life science oriented chemistry, this is used extensively because many phospholipids are medications, for instance, against cancer, or they're used to produce capsules, for instance, for vaccines, for example. And so this is one of the most developed chemistry to synthesize phospholipids, and we just adopted that and produced phospholipids of different kinds as capping ligands for the nanocrystal. So this work will be published in the next couple months. Let me show you another aspect which is possible with perovskites and not easy to do with anything else, which is now you can also engineer the perovskite itself. Perovskite lattice is very soft. So you can actually displace some of your inorganic constituents with organic ones, maintaining the lattice. So the lattice will not collapse even if you displace up to 10% of the core material by another organic material. And so you can keep the nanocrystal size, you can, but you will drastically modify the electronic structure. For example, you can actually engineer such materials, these hollow perovskite materials, what you see on the screen, that you will have exactly same emission color, but you will have different radiative rates. And we have used it, not shown here, but we have used it to engineer the unicolor security tags by inkjet printing. You can find it in this publication from the last year. So this brings me to a summary of the optical properties, and the part 2 of my presentation. So by now we have all these luminescent nanocrystals, and as you have noticed, they can be used for television displays, and indeed there are companies worldwide which now develop prototype displays with perovskites in China, also in Switzerland. But looking in future, perovskite nanocrystals are also extremely interesting as quantum light sources. And I will briefly cover that, but more about our vision in that regard and challenges you can find in the recent review articles. So very early on, from 2016, our colleagues within Zürich at IBM, they began looking at single particle emission with perovskites. So here you see single particle spectrum, and somehow my screen is freezing. 1 second. Yeah, now it starts to react. Okay, so here you see the emission spectrum from a single quantum dot as a function of time. So it's a stable single photon emission. There is clear single photon emission confirmed by the anti-bunching experiment, and these quantum dots do not blink much. Just to put it in perspective, before the perovskite quantum dots, all the other kinds of the colloidal quantum dots have been unstable, they blinked a lot, and at such large sizes, they had not been single photon emitters. So what this led us to, and let's look at some other important properties, which are very specific to perovskites. One is that at low temperatures, they're extremely fast light emitters, one of the fastest emitters that you can find. Unlike to conventional quantum dots, which become much slower emitters, as you call them, so their radiative rates are in microsecond range because they begin emitting through the dark exciton state. Perovskites emit through the bright exciton state, also at low temperatures, and with sub-nanosecond radiative rates. And what was also extremely exciting, and this is essential for the future, is that they can retain at low temperatures their exciton coherence for a decent fraction of their radiative lifetime. And so basically they are reasonably coherent emitters at the single photon level, and this motivates to build collective states where potentially these single emitters might couple into larger aggregate states with coherent emission as a collective state. And so one way to design such aggregate states would be to self-assemble quantum dots into superstructures. And so here again, we look at the history where people have used a drying-mediated self-assembly of nanocrystals to generate long-range ordered superlattices. You simply can take a monodispersed colloid of nanocrystals of spherical shape. You can dry out the solvent, and you will end up with a superlattice. This is known for cadmium selenide for several decades now. How it works is because it works that easily only for the colloids which are so-called sterically stabilized, which is apolar capping ligands like we have for perovskites. And so that the particles experience very short-range repulsion, but they rather are non-interacting at the longer distances. So this steep interparticle potential in a good solvent. So this occurs also when you choose the solvent correctly. It has to be apolar small molecule solvent. When you have that case, nanocrystals will undergo spontaneously into self-assembly. They will undergo self-assembly into ordered states because at the late stage of drying, they maximize the free volume entropy, essentially. And even though they sacrifice the configurational entropy, you still get overall small entropy increase through the conversion into the ordered state at a very late stage of drying. And then the solvent evaporates fully, and then you are locked into a superlattice. And for spheres, you will end up with the structure which is one of the densest sphere packing, which is face-centered cubic or hexagonal closed packing. Now you can ask, what about cubes? For cubes, it's much simpler. Cubes form supercubes, which is 100% space occupation. And so naturally, these were the first superlattices whose optical properties we examined at low temperatures. So these large supercubes can be as large as 10, 20 micron, and they can be produced as single entities on the substrate. And this is electron microscopy of these. Now, when you cool to low temperature, what was super exciting about 5 years ago, when our colleagues have observed these sharp emission bands at lower energies than your normal excitonic band, which suggests some coupling. And this is a coupling, incoherent coupling of these entities. And then as you start increasing the power density for your excitation, you start seeing the shortening of the radiative rate without losing the quantum efficiency, which means that you have pure acceleration of emission. So what happens is that your initially incoherently excited quantum dots build coherence across themselves if they are in a sufficiently close proximity. And for this effect, they have to be something like within the half a wavelength from each other. So if in that volume, you have a sufficient number of photoexcited quantum dots, they start building coherence across themselves and establish large multi-particle dipoles, which emit coherently then, and which emit light and with a faster radiative rate because they have a higher oscillator strength. So basically, as you can imagine, the higher will be the density of these photoexcited dots, the higher is power density for your excitation, the larger will be this coherent state, and therefore the faster will be the emission, and that's exactly what we see. And in addition, because it takes time to build the coherence, and then it emits, and then it circles, you have this oscillations in the radiative rate, and you have dynamic shift because as you radiate, you lose the stabilization energy from the coupling, so it goes back to the bluer energies, and you nicely see these oscillations if you compare it the radiative decays at different excitation densities, and you also see this linear dependence between light in and light out. and which speaks for the purely radiative nature of everything that you observe. So this property is called superfluorescence, and we were very excited to observe that because it's simply the first chemically produced quantum dot system which exhibits this property. So far, it had been observed in very few cases, which is epitaxial quantum dots of one kind, as well as some of the atomically doped alkali metal halides, or even in some of the gases such as hydrogen fluoride. But now you have a solid state system where you can tune this property potentially through composition, through size, through nanocrystal assembly, and you can basically engineer this property. It's not that you just can observe it. And so we were extremely motivated to try to engineer this property further. And so then we thought, okay, as chemists, we can build more complex superstructures, not only simple cubic packing into supercubes, but we can combine perovskite quantum dots with some other materials or dielectric spacer quantum dots such that we can mutually orient the perovskite light emitters and see how that helps or not to build these coherent states, these collective states. Again, back in history, roughly 20 years ago, the first examples of binary nanocrystal self-assemblies had been reported by Chris Murray and his colleagues, who simply mixed two spheres of different sizes, sterically stabilized, as we discussed. And then upon solvent evaporation, they have observed these crystal structures, which are identical to what you know in the atomic world, except that it's now built of nanocrystals as artificial atoms. And so when you speak of spheres, you can observe these types of structures of different kinds. And in the inset here, you see the actual crystal structure analog in the atomic world. So it can be as simple as sodium chloride or as complicated as some intermetallic type of structures. And so in our work, we set to ask ourselves, okay, we have cubic shaped nanocrystals. Will that matter? And then you look in the literature and you find that nobody actually ever made binary lattices where you mix non-spherical nanocrystals, particularly cubic ones. And so I have brilliant students, and one of them, Igor Chernyuk, has made titanic work on basically on first producing the library of these shapes with extreme control of the monodispersity, cubes, spheres, truncated cubes, disks, thin disks, thick disks, and he combined cubes with all kinds of other nanocrystals, trying to build multi-component superlattices. It's basically at the limits of what synthetic chemistry can do at the mesoscale. And so what we expect is that perovskites actually are soft cubes. Imagine the nanocrystal, it has this very rigid cubic core, and it has these ligands, and ligands are soft. They can bend, they can deform. So there is certain softness, and the smaller is the cube, the greater is the softness because the volume occupied by the ligand increases. So to minimize the softness, we actually stick to the ligand which is shortest of all, which can still provide colloidal stability, which is the one I already showed you in some of the previous slides. And then we took two kinds of cubes. One is the bigger one, which is harder, and the smaller one, which is softer. So the effective size of the cube is the core plus the ligand length. And then we thought, okay, this lattice is known for spheres. Can we make it out of cubes? And now the rule of thumb here is the following, that you need to mix the sizes of your spheres or a cube plus sphere in a certain range where the resulting packing density for this lattice will be the highest. Because unlike two atoms where you cannot really change the size, here you can. And so here you see that, for instance, when you mix two spheres, they will have high packing density only in a specific size range. And only then you will have this lattice more stable than the phase separation into single component lattices. So basically you compete against phase separation, and you will win this competition only if your resulting lattice is denser or similarly dense. So with cubes, it's actually even easier because the cube of the same diameter as the sphere is larger. And so you can get actually higher packing densities when you switch from a sphere to a cube. And we tested this, and we indeed, and there were theoretical predictions that this is the case, even years before our work. And indeed, we observe a superlattice where the perovskite cube is surrounded by these spheres of iron oxide or another compound, or these, yes, in this case, it's iron oxide, but also can be some dielectric material. Excuse me, the computer seems to freeze a little bit. Just a second. Okay, so yes, it's another kind of, it's a dielectric sphere, sodium gadolinium fluoride, and you do get again the same type of a crystal structure. Now, we have observed much more interesting structures, but before you will understand why they form, let me also bring your attention to the fact that your ligand shell is not only deformable, but it can deform in a very specific manner. As that was observed years ago and was invoked to explain the stability of some of the binary all-sphere assemblies, which would otherwise be hard to explain. So what can happen is that when two spheres approach each other, the smaller one, the ligands on the smaller one can bend away, can create these vertices, and therefore they can allow a more compact lattice, so that these two spheres can approach each other closer when one of the spheres can bend away their ligands. And so this is stabilizing the higher packing density. So if that happens, you can expect that your overall stability of the lattice will be higher because you can stuff much more material per volume, per unit volume. And for spheres, this has noticeable effect only in those structures where you have small coordination numbers. If the coordination number is high, there is simply no space to bend away these ligands. Now, when you go to anisotropic shape or less, it's actually isotropic, but sharper shape, cube. Imagine a cube impinging the sphere with the edge. And so this sharp contact will very likely lead to the bending of the ligands so that the cube and sphere can come closer to each other. By the way, this must happen also when two cubes approach each other through the edge or through the corner. And so this happens indeed. And this has a stabilizing effect so that you can have lattice which is denser than without the ligands bending. And so that's unique property of these sharper shapes, which allows to observe new crystal structures. And let me show you one very prominent example of such a crystal structure. Look at this mixture of two spheres, which I already tell you had never been observed experimentally. So only atoms form this crystal lattice, but nanocrystals with, at any size ratio, two spheres never crystallize in this crystal structure. This is nickel 4n type lattice, which is basically derived from the perovskite lattice when the facet and the center atom is the same. Now, again, computer is freezing again. 1 second. I probably will stop sharing and restart the presentation. Okay. Yes, it should work now. So, so, all right. And so, if you compute the packing density at any size ratio, this lattice is indeed unstable. But now, now when you mix a cube and a sphere, you do get the perovskite type lattice, because already without any assumption of ligand deformation, at least it's in some narrow size ratio, it will have very high density. But if you assume in addition the ligand deformation, you will expect even broader range of stability. And then we checked this range experimentally, and we indeed observed that cubes and spheres do form such a lattice, and they form it very, this lattice is very much favored compared to the phase separation. So you end up with a very nice, very clean yield of this structure. It outcompetes phase separation by far. And let me just, let me show you that you can see it nicely in three-dimensional electron microscopy. You can observe it by all the techniques which proves this lattice from X-ray diffraction to electron diffraction to direct observation in transmission microscopy. So it's a very peculiar example because you build perovskite superlattice out of perovskite-based nanocrystals. And so just for the last few minutes, I will show you that indeed these structures do show superfluorescence as well. So, and what is more interesting is that you indeed, if you compare different kinds of superlattices, you start seeing correlation between the structure and the superfluorescence that you observe. For example, in one case, you even see the blue shifted superfluorescence. In another case, you see the superfluorescence threshold for the appearance as a function of the dielectric sphere diameter. And in another case, you see that you do not observe superfluorescence because the volume fraction of these, how many particles of perovskite you have per volume is here much smaller than in such type of a superlattice. So you start correlating your superfluorescent property with your structure. And to show you yet another possibility is that you can start building fully ternary lattices, where also the center cube can be a different type of cube. You can put if you take a mixture of smaller cubes and larger cubes in a specific particle number ratio and size ratio, you can actually build a lattice where preferably a bigger cube will go into the center of a unit cell, because crystallographically this site is a little bit larger, and therefore for geometric fitness this cube will go over there. So this is very tedious experimental work because you need to control the sizes very precisely, but once you do that, you can produce such ternary structures as well, and you can fully characterize them. And we have discovered a whole bunch of new lattices, which I will skip because of the time matter, but I will just tell you that also when you combine cubes and disks, you again will observe new lattices, which you cannot see when you combine spheres and disks, because these structures have higher packing density. As you can see, for instance, if you compare the space filling curves for this case versus the space filling curve for the sphere disk mixture. And so we have discovered the library of these ones for different sizes of disks and sizes of cubes. And again, there is a structure property correlation in the superfluorescence. Now, this is a structure of calcium carbide type, where you now see that that you can occupy one lattice side by two cubes, and then you will have this very nice lattice. So for those who are interested to see details of that, there is a recent publication where we have covered all the structures which we have observed so far in one article. So for those who care for that, you can see the details in that paper. and I will skip the rest and show you that you can now start co-assembling the perovskite nanocrystals with molecular large giant inorganic clusters, and that's also ongoing work where we generate superlattices which are sort of at the interface of the atomically defined world, which is clusters, and nanocrystals which are non-atomically defined. And that is the future work. And with that, I thank you very much for your attention. I'll be happy to answer any question related to this work.
Maksym, thank you very much for this very comprehensive and intriguing talk.
Thank you.
Now we can take some questions. Please ask questions or send questions through chat area. Yes, questions, please.
I see one.
Yes. Yes, sure, you can ask questions. Serhat, please ask. And another question, please, came from Oğuz Gülseren.
So the question from August: what is nature of aggregate states that led to single photon emission, excitonic state? So just to clarify, single photon emission we get from a single quantum dot, not from aggregated states. So we produce a sample where the individual dots are very well separated on the substrate, so very diluted system, and then we look with the microphotoluminescence at a single particle, and basically that is how we observe. And yes, it has excitonic nature. So when you have defects, the luminescence is quenched, and so you don't see any emission. And here whenever we see single photon emission, it comes at exactly the energy of the exciton. Perovskite doped glasses. Another question is from Aytac about the perovskite doped glasses. Very good question. In literature, you're right, there is an increasing number of works where people produce perovskite quantum dots by melting the precursors together with the precursors for the glass. And then when they anneal it, they produce perovskites in the glass, similar to one of the actually very first examples of quantum dots in the history 40 years ago. So this is indeed a very good idea. And I believe that such perovskite in a glass systems have intrinsic advantages potentially because the perovskites are very well protected from water and the environment. The only problem that I see is that, because I keep up with the literature on that, because I thought we may want to do that too, is that the quantum yields which people report are actually lower than in the colloidal system. The best quantum yields I've seen are like 50, maybe sometimes 70%, but usually less, like 10 to 30%. And that can be explained by the fact that in this process of annealing, there are other phases formed which absorb light, and also the defects are probably not, the trap states are not well taken care of. So to me, this is the only problem. Okay, now the next question I see in the chat, from Roman, where I can find these papers and perovskite related topics. What is luminous intensity of these QDs? Can they be used in place of LEDs and laser and optic fiber? So, to make it short, if you don't find papers, write to me. I will send you the needed papers. And your specific question is luminous intensity of these QDs, and can they be used in place of LEDs? Of course, they are used in LEDs as actually as electroluminescent layer as well as down converting layer. So people do measure, do use them both ways. Serhat wrote their question. I measured decay time of cesium lead bromide nearly 20 nanoseconds. Your research shows it about 1-2 nanoseconds. My QD sample was from a company based in the UK. That means we had different type of or another problems that they had. Very interesting question. This quantum yield of 1 to 2 nanoseconds is what we see in the colloidal dispersion when the dots are non-interacting. When they start to interact, when you make film, you can have electronic delocalization or reversible trapping of a charge, and altogether this may lead to apparently longer radiative rates. I assume you measured actually these 20 nanoseconds not in a colloidal dispersion. Another factor which matters is the size of quantum dots. So the larger dots will have a bit longer radiative rates. Then the next question: can you give us details of the procedure for compositionally ternary ABO3 superlattices on slide 54? Oh yes, you should write to us, and we can send you the details. It's also published in the paper, but if you find that the paper doesn't give you the needed detail, please write to me or to the first author of the Nature article, which is Igor Chernyuk, and he will gladly provide you the needed detail. We will be happy if you can. If you are working on reproducing that, we will be happy that you do reproduce it, so that your result is to your satisfaction. Now, Serhat writes, I tried to use them as a scintillator for X-rays. My answer to that is that I hope you had good results, but my doubt about scintillators generally, based on perovskite, is that if your goal is to make a scintillator with good light yield, you need to have thick absorber layer. And with perovskites, which have very small stock shift between the emission and absorption bands, there is a lot of reabsorption. So I'm a bit skeptical for scintillator applications of them in those applications where the light yield is the key. Muge asks the question about if you can ask if they can send us an email, and of course you can always send us an email about the analysis of perovskite quantum dots. I'm glad to see that there are people interested in this research area. Okay. Anyone else having questions? Yeah, so Serhat wrote that, of course, you can, yes, please send us email with whatever you would like to discuss about the perovskite quantum dots.
Maksym, there's another question from Yavuz. Can we change fuel oil energy? Before the last one.
Can we change fuel oil energy with nanocrystals, hydrogen energy, if even we can? What is the point of selecting fuel oils against nanocrystals? Yavuz, I apologize, but I have difficulties to understand your question. maybe you could speak up or rephrase it somehow.
More questions, please. Yeah.
Yavuz, maybe you can turn on mic or. Okay, I go to the next one, which is from August. If I'm not wrong, usually bulk perovskite stable at orthorhombic structure at ambient condition. You have cubic, is that because of nanocrystal size? So, August, a good point. I actually did not say that our perovskite have cubic crystal structure. I just used cubic structure for simplicity to depict the crystal structure overall, but you are right. It's never cubic for cesium. It's actually orthorhombic. So the halide lead bond angle is not 180 degrees. In one of my slides, I had it in an orthorhombic setting, but in a slide which is general for perovskite, I used cubic. But cubic are only the formamidinium based. Methyl ammonium are tetragonal and cesium based are orthorhombic at room temperature. So you are completely right. We actually have proof that they are cubic at any size. Cesium lead bromide. That they are orthorhombic at any size. Cesium lead bromide. And formamidinium are cubic at any size. So just like the bulk at the same temperature. So your question, so Yavuz rephrased their question. So about energy production with nanocrystals and what is the point of using fossil oil, I believe. Well, oil is, has very high energy density. Now with probably you refer to photochemical or photoelectrochemical hydrogen generation. I guess it's a meaningful area, but I'm not the right authority to comment on that. Yeah, we don't work in that area in the hydrogen generation by photo or photoelectrochemical means. Yeah, that would be my answer. I actually like this format to read. It's to read the questions. So, yeah.
So, if no more questions, perhaps we can take your final comment, Maksym, and then close the session, if you don't mind.
Okay. Final comment.
Yeah.
I didn't think of that, but so my final comment would be that probably I will comment on perovskite nanocrystals, and I would say that those who wish to enter this research area, I think there are still plenty of problems to work on, and many more than we had 6 years ago, as usual. The more you progress, the more work is out there. Applications are huge because you can use these materials in displays, you can use them as scintillators, you can do potentially photocatalysis with them. They are very strong energy harvesting system. There is no real lead-free alternative for them. I didn't comment on that today, but there is not a single system that can compete with lead-based perovskites in terms of emissivity or absorption amongst metal halides. Now, lead-based perovskites, quantum dots they are not necessarily better in every regard comparing to indium phosphide or calcite. Each of the systems have their own merit. For instance, I didn't show anything on light-emitting diodes with perovskites because I believe that they are inherently unstable because of electrochemical activity of lead 2+. that's where cadmium-based QDs will have higher potential. But for the applications where you use down conversion, such as LCD displays, I think perovskites will be commercialized in the next couple of years as a television display emitter. I think there is plenty of work in terms of multi-body phenomena and in terms of single dot emission. So for physicists, for example, there is plenty of work to understand these semiconductors. They have very strong exciton phonon couplings. They have very interesting polaronic effects, and so the physicists all over the world increasingly get excited with this material. So my message to chemists among you is that don't be shy to start working with these systems, and if you need any question, ask. And physicists, please don't hesitate to ask for a sample or any help that you might have. Right. So yeah, that was my last message on this topic.
Thank you.
And
so
thank
much.
you all for gathering today for this seminar. I had very good memories of my visits to Ankara, to Bilkent University, to Istanbul also. And as soon as I will travel full speed, I will go back to Turkey for sure. It's very exciting country, very rich in talent, young people who are really, really good students and good scientists.
Thank you so much. That was a great pleasure to listen to you this evening. I hope we will see you in person in the nearest future. Take care of you.
Thank you very much.
Bye.
Bye-bye.
Bye-bye.